mean, it kind of sucks about 5 pages of that chapter.
Okay. So here's where we left off on Friday.
I have one in my hand, and that's it. No, I know you do. No, we have 10 days of school. Hold on a second, look. We got to pull it out. Roark, do you have a pencil I can borrow? No. Wine. It says Brown Valley on it.
Oh, it's probably, yeah, it's probably used for shaming then.
Alright, so, number 4 here. It says you should be able to list the number of electrons in each orbital, number of orbitals for each type, and types on each energy level. Now listen. This is not as hard as you make it. This is unit 3, yes. Right? Yes. Okay. So, number of electrons in each orbital. Remember, no matter what, each orbital has 2 electrons. Okay, number of orbitals for each type. So remember, they're basically the odd numbers. There's 1 s orbital, there's 3 p orbitals, there's 5 d orbitals, and there's 7 f orbitals. So it's just the first 4 odd numbers that correspond with s, p, d, and f, those shapes. Okay, and then the types on each energy level. This, remember, we can look at the periodic table. Because the setup of the periodic table actually shows us So remember, as far as the setup of the periodic table goes, these are the energy levels for the most part. Okay? So, this helium, remember, is the one that's a little bit out of place. Okay? The helium we put over here because it's a noble gas, but as far as orbitals go, it would be much better suited over here. These are all s orbitals, these are all p orbitals, these are all d, and these are all the f. And so just by looking at the line, you can tell the first energy level only has an s orbital. Okay? The second energy level, so the second row here, has an s and a p. These all correspond for electrons that would fit into the p orbitals. The third energy level has an s and a p. Okay? And then we have to remember that the d orbitals lag by 1. So on the fourth row, the reason why these are set up this way is to show us the way in which they fill, right? When we're writing an electron configuration, which we'll be talking about next, it goes 4s, and then it goes to the d orbitals, but remember, d always lags by 1. So even though this is on the fourth line, it's technically part of the third energy level. Even though this one is on the fifth line, it is the fourth energy level. So the third energy level, the fourth energy level, these are still the fifth energy level, these are still the fifth energy level, it's just D's lag by 1. Okay, so this would be the fifth energy level and this would be the sixth energy level. Now the F's, remember, are really supposed to be in here. The periodic table is drawn in a way that it fits nicely on a regular sheet of paper, but technically these should be in here and all of these should be moved over. The thing you have to remember is that f orbitals lag by 2. So even though these elements should be right here on the sixth line, these are technically part of the fourth energy level. Okay, so S, you can read off the straight out the periodic table. P's, you can read straight off the periodic table. The D's lag by 1 and the F's lag by 2. That's what it means for the types on each energy level. Okay? But it also kind of increases as you go up. The first energy level has an S. The second energy level has an S and a P. The third energy level has an S, P, and a D. The fourth energy level has a S, P, D, and F, and then 5 and 6 both have all of them as well. It's just they're out of order a little bit. Okay, so that brings us to number 5, write full and abbreviated electron configurations for any atom on the periodic table. Probably the best way to review this is just to write one out. So, let's try selenium. Number 34 on the periodic table. Now remember, one thing to look at, there's 34 protons here. That's what this number means. And so that means we're writing for neutral atoms. There's going to be 34 electrons too. So when you're done, a way to make sure you haven't left anything out is there should be 34 electrons in your configuration. Well, that's the abbreviated one. You got to be able to do both. Okay, so we're going to do both for selenium. So we start on the periodic table. On the first energy level, it's going to be filled. So that's 1s2. Remember, these show how many electrons. This is the whole notation here is first energy level. In the S-shaped orbital, there are 2 electrons. Okay, that's the first row on the periodic table. Then we go down, and lithium and beryllium there tell us that we go to 2s2. On the second energy level, in the S-shaped orbital, there are 2 electrons. Okay, then we go over, and we see going across, there's no D, we go over to the P's. So this is going to be 2p6. On the second energy level, in the P-shaped orbital, there are 6 electrons. That takes us through neon there. Okay, and then going on to the second line, now we're on the third energy level, 3s2. Again, we skip over to the P's, 3p6. That takes us through the third line there. Now we're down at potassium and calcium, so those are our S's in the fourth energy level. So 4s2. And then here's where we have to be careful. Because going from here, it doesn't go to the P's, it has to go through the D's, but we have to remember that D's lag in energy level by 1. So this is 3D. And how many electrons fit in the D energy level? 10. Okay, because remember there's 5 orbitals, and each orbital holds 2 electrons. So 3d10 takes us all the way up to zinc. And those, because we know we're filling in all those orbitals up to there in the blocks, we don't have to really worry about that. But now we have to go, okay, there's only going to be 1, 2, 3, 4 electrons in that next orbital. So these are P's. They're on the fourth line, so this is the fourth energy level. In the P orbitals, the P-shaped orbitals, there will be 4 electrons there. So this will be back to energy level 4, P4. So this is the full electron configuration for selenium. Okay, now the abbreviated, remember we go back to the last noble gas. So looking backwards, the last noble gas that we went through is argon. Okay, argon corresponds to the first 18 electrons that are on there, up through the third p orbital. So basically all of this right here, if we were to write argon's electron configuration, it would be this up to this point. And so in the abbreviated, we can put the brackets around argon, and then put the rest of the electron configuration. So 4s2, 3d10, 4p4 from that point. Now, on the final, I guarantee I will give you an element and ask you to write both the abbreviated and the full. So you have to be able to do them both. Yes, that should have a check mark next to it. All right, on to number 6. It says you should be able to find the number of valence electrons and draw electron dot diagrams for different atoms on the periodic table. This is the part we're going to focus on. You can cross out electron dot diagrams. I will not ask you to draw an electron dot diagram. But we should be able to find the number of valence electrons. Okay? However, the number of valence electrons, as far as the way we're going to use it, really only corresponds to the first 3 energy levels. Okay? And all you do is you figure out how many electrons are in that energy level. So, for example, silicon. Okay? How many electrons, so silicon right here, we can see that its last electron is on 3rd energy level. How many total electrons are in the 3rd energy level? 1, 2, 3, 4. So you literally define valence electrons. All you have to do is count from left to right on the periodic table for the element. So nitrogen, 1, 2, 3, 4, 5. And we can see nitrogen and phosphorus are going to have the same number of valence electrons.
You're not going to give us anything below 3.
For as far as valence electrons go, no. Yes, silicon would have 4, carbon would have 4, boron and aluminum would both have 3. Neon and argon would have 8. And then helium right here, remember, don't get mixed up that it's in that row. We still count from left to right. Helium's only got 2. Okay, any questions there? All right, let's go on to Unit 4. Wait, did I have 7, 8, or 9? Did I just forget to scroll down? Oh, no, I didn't circle those before. Yeah. Oh, were you not here Friday? Okay, sorry. Yeah, on each chapter I'll circle the ones that we need to focus on. The rest of them you can kind of ignore. Yep. Okay. Yeah, you'll see that here. It's not exactly the same as a circle, and I'll explain why here. For Unit 4, you should circle everything except number 5. And we will put an arrow next to number 5. Now, here's why a circle and an arrow are not the same thing. Because for number 5, it's good to have an overall, it will help your understanding of the rest of this stuff if you have an overall idea of atomic radius, ionization energy, ion size, and electronegativity. It's not like we're just saying, oh, you don't need to know that information at all. But I will not have any specific questions where I say, which one of these ions is bigger or which one has a higher ionization energy. So that's why I put an arrow next to it. You won't see a specific question about that, but it's, I wouldn't, when you're studying, I wouldn't necessarily just completely skip over it. Yes?
So you're saying that all the ones that don't have arrows, like 1, 2, 7, 8, and 9 on the last one, we don't need to know whatsoever?
Right. Those are ones that I really won't ask you anything about. All right, number 1 says explain periodicity and the observations that led Mendeleev to develop the periodic table. So really the basic thing here that you need to know is that the properties repeat themselves, right? Properties of elements repeat. Not yet, no. So when we look at the properties of silicon and carbon, or oxygen and sulfur, we see they have similar properties. Not the same, there are differences, but they are more similar to each other than other things. Repeat. Properties of elements repeat. So remember, Mendeleev organized his periodic table and left holes in there for things that he figured we hadn't discovered because there wasn't really anything else that matched up as far as the properties go. Now, the thing that we need to relate this to and make sure we know that Mendeleev didn't know because they didn't know anything even about atoms back then, specific atoms. Why do carbon and silicon have similar properties? Why do fluorine and chlorine have similar, and bromine have similar properties? They have the same amount of valence electrons, and that's the point. So the whole setup of the periodic table, even though Mendeleev didn't do it on purpose that way, because it's related to the properties, it's based on the number of valence electrons. Remember, the whole point is valence electrons are ones that can actually form chemical bonds. So when we look at sulfur and we say, well, sulfur's got 6 valence electrons, even though it's got 16 electrons, remember 10 of those are in the inner energy levels, they're shielded, they can't interact, they can't bond. So it's the 6 valence electrons that really make sulfur act the way it does. And because oxygen is in a similar vein, it's got 8 electrons, but 2 of those are shielded, so it's got 6 valence electrons. It's going to behave in similar ways because it has the same number of electrons that can form bonds. That's not true. That's not true at all. You're not everyone. Which movie is that? Yeah, it's French. That one I haven't actually seen. Yeah, I have no idea. I don't know. Let's focus on this. Number 2 says you should be able to identify elements in the metal, non-metal, and metalloid groups. Okay? So remember, that's fairly simple. We have this stair step here. I even drew it out on this periodic table so that you can see it. All of this crap is metals. These are the non-metals. The things that touch the stair step are considered metalloids. We have a couple exceptions, though. Exception number 1, aluminum, even though it touches the stair step, is not a metalloid. It is a metal. So that's exception number 1. Exception number 2, hydrogen, even though it's over here to the left of the stair step, it is definitely not a metal. It is a non-metal. Remember I said before, hydrogen, as far as the periodic table goes, hydrogen really almost should just be kind of off on its own. Aluminum. I mean, aluminum's a metal, right? It definitely is.
Wait, okay, so to the left are all metals.
Mm-hmm.
Touching are metalloids.
So if you remember on the test, or you can go and look at it, I had like a list of different elements, and I just said, tell me if it's a metal or a non-metal. I would expect to see something similar like that.
Yeah.
The aluminum is the only one that touches the stair step that we're going to consider an exception. Yes.
Number 2 is the second one.
Yeah. Okay, and similarly on number 3, the different subgroups. So remember, these are the alkali metals. These are the alkaline earth metals. The way I always remember that is alkaline earth is 2 words, and this is in the second column. Alkali is 1 word, and this is in the first column. But then also halogens, okay, noble gases, that one you guys will probably remember, and transition metals. Halogens are row number 17 there, fluorine, chlorine, bromine, iodine. Now the transition metals are the ones all in the D block, and technically the F block too. Mm-hmm. We don't have specific names for those. Mostly the reason why that is because of that stair step. They differ in properties so much that we haven't really said, oh, this is a whole group. But sometimes We call this stuff in the boron group or the carbon group or the nitrogen group or the oxygen
Wait,
group.
where are the transition in halogens? Transition is the B block and S block.
Yeah, these are all the transition metals, and the halogens are right here. Halogens are the second to last column there.
Right before the noble gas.
Yes. Halogens are all elements that have 7 valence electrons. They get one extra. Yeah, along these lines, where I give you an element and I ask you what group would it belong to. Or maybe vice versa. Maybe I'll say, give me an example of an alkaline earth metal. Maybe. It's harder for me to grade, though, because then I got to think about it instead of just... if I have a choice, why would I make it harder for me and easier for you versus the other way around? Have you met me? All right, number 4, you should be able to explain that the periodicity of elements is tied to similar electron configurations. I mean, that's a little redundant from what we talked about up above, so that's fairly self-explanatory. Yeah, that's what redundant means. Okay, so the whole point is that the way the periodic table is set up is based on electron configurations. All right, number 6 says you should know what an ion is and differentiate between an anion and a cation. You don't know what it is? What is an ion? A charged atom. So an ion is an atom with a charge. Now, the thing to remember is the only way you can change the charge of an atom is by moving electrons. Electrons can be taken away, electrons can be added, but you can't add or take away protons because that would change the element and it's the nucleus, and there's a whole lots of reasons why. So it's all about electrons. So if something gains electrons, it'll be negative. That's fairly self-explanatory. But students get mixed up. Oh, it's positive. It must have gained positive charges. No, it lost electrons. It lost a negative charge to become positive. Makes it negative, loses electrons, makes it positive. And we have specific names for those things. A cation has lost electrons, and an anion has gained electrons. Cations are positive, and anions are negative. That is the way to remember it. And also, a T looks like a plus sign. So there's that. Okay, now, one thing here before we move on to the next section that didn't really get put into these specific notes, and I probably should add it, is we should be able, and you guys are pretty used to this, so I don't think it's a big deal, but we should be able to look at the periodic table and figure out what type of ion a certain element is going to form. So remember, all of these are going to form a +1 cation. All of these are a +2 cation. They're going to lose electrons, right? Lose 1 electron, lose 2 electrons. These are going to lose 3 electrons, become a +3 cation. These, remember, do not ionize. So they're not going to gain or lose electrons. They're always going to form covalent bonds. So we don't really put anything up there. Yeah, these, remember, are weird because they can be +5 or -3 depending on the situation. So sometimes they can gain 3 electrons, sometimes they can give up 5. Always give up 2, always gain 2, always gain 1, so these are always -2, these are always -1. And remember, noble gases, if you're just working on ions, you could almost leave off that whole column on the periodic table because they will not ionize, they will not form bonds. I talked about that right at the front, just that those are...
Oh my god. When's this test? Friday, Monday? Once we have to do that first.
Yeah, the first part of this test is going to be Friday.
Is it gonna kick my ass?
Yeah, but then we went to get,
The second part on Monday.
Yes.
I don't give two about the movies.
it's a week and a half of school off.
I don't give two
Hold on Monday.
I mean,
next week and then the week after.
since you guys are all going to be gone Wednesday, I am not against just taking that day out, and then just a minute, listen. El Toro. So, and just moving the rest of the days back, then we would have the test on Monday and Tuesday. So I'm okay with that.
That's a good plan.
It would make more sense. So we'll do that.
Sure. Then I have to study anyway my college battle.
All right, so Monday and Tuesday will be the final. Everybody back there hear that? Monday and Tuesday?
All you kids sleeping back there?
I was mostly looking back there. All right. Let's go on to the next chapter.
No. Writing formulas end my life. Only have report that.
Yep, report it. He's doing it right now.
Email it. How come you took the rope down?
Uh-oh. All right, give me just a minute. I forgot to put up the next chapter's study guide here.
Yeah, I really don't want to. I'm falling way behind in math. I got homework yesterday. I was up till 1 o'clock in the morning doing homework, and I didn't even get it all done.
You were doing homework till 1 o'clock in the morning?
I started at 8.
I did homework on it.
I had homework in every single class. Yeah, well, you're gonna have to help me a lot with math.
I got ellipsis on.
Yeah.
2 problems on a hyperbola.
I did not have it.
Hyperbola.
Picture's gone.
No.
Yeah, he's gone.
Watch the video.
Quiz on what?
No.
With the
No. Screw it. No, for sure, write it down. True. If it was Kim, we could have talked to him.
There was one time in sociology, the seniors were talking about how much money they could make selling drugs when they were looking at like a camper to buy, and she reported it to my dad. Who? The senior. Breached it? Reported it? Yeah, breached reported it. That they were talking about selling drugs. We should make her report something. But she didn't report when we put markers up like the Twin Towers.
Actually, she thought it was
an airplane at them.
Oh yeah, you can do it. Hunter throws the paper.
That was me. I wasn't even in there. I was holding it.
I even threw it.
Yeah, you threw it.
I was holding both markers.
I was even in those.
Oh, fuck! So he dropped the markers. Put it away. I did not think you were gonna do that. I'm like, oh boy. You get like.
I was even there.
Who's all your full hunters?
Okay. Number 5. Chapter 5. Circle 1. Hey, shut up and listen. Circle 2. And 3. And 4. And 5. And 6. However, if you notice,
And draw arrows next to that.
what do we notice about number 1?
Oh!
It's exactly the same as the one we just talked about. So, we don't really need to talk about that one for completeness.
I'm Xing it out.
Because we just talked about that on the last chapter. So, know what an ion is and differentiate between anions and cations. Okay?
Can't go wrong when dropping on the call.
Now, number 2, I don't know, I wasn't thinking about the next chapter. This part right here, be able to predict the charge of different monatomic ions, that's what we just did, right? So based on the periodic table, where they line up, +1, +2, that's the monatomic ions. So we just talked about that too. Okay.
Draw the line there so
We just talked about this. +1,
Yep.
+2,
That's all that means?
yes.
Okay, I'm going down right here.
Monatomic means one atom. Now, explain the movement of electrons to form specific charges. That really just comes down to whether they're losing or gaining and how many electrons. So, if I said how many electrons would oxygen, or actually the way I would phrase it actually is probably explain the movement of electrons for oxygen to form an ion. And so you would have to say that oxygen is going to gain 2 electrons to form a -2 charge. Okay, if I said explain the movement of electrons for aluminum to form an ion, you would say aluminum is going to give up 3 electrons to form a +3 charge. All right, number 3 says explain how ionic bonds form. Remember, ionic bonds form from a transfer of electrons. They're going to form ions come together. There's going to be a sharing, a giving up of electrons from one and a taking of electrons from another. So, for example, sodium and chlorine, when those atoms meet each other, the sodium is going to give up an electron. That electron is going to be transferred over to the chlorine. That gives this a -1 charge. That gives this a +1 charge. And that's why they form an ionic bond. Remember, ionic bonds basically form, we say the transfer of electrons, and that's true, but it's the attraction of the cation and the anion. It's the attraction of the positive and negative ions. The anion and the cation are attracted to each other because one is positive and one is negative, just like little magnets.
James, remember last time we played that? Wait, did we play in it? Yeah.
We played there and also.
All right, number 4 says you should be able to write formulas of ionic compounds. So, for example, aluminum and oxygen. All right, shut up and listen. Aluminum and oxygen. When these two get together, there's going to be a transfer of electrons. Remember, aluminum is going to lose 3 electrons to form a +3 cation. Oxygen is going to gain 2 electrons to form a -2 anion. So we have to figure out how are these things going to go so that there's a full transfer of electrons, so that oxygen is able to gain 2 and aluminum is able to give up 3. And yes, we use the cross-down method to figure that out. So this formula for aluminum oxide is going to be Al2O3. It takes 2 aluminum to give up enough electrons. Well, when they're in a compound like this, they shouldn't have the charges anymore, right? Now, if they're disassociated apart from each other, then you would have to have the ions. So remember, in a compound, in an actual formula, you don't have the charges. Okay, explain what a polyatomic ion is. So something like SO4 that has a -2 charge. So the whole point, remember, is this 1 sulfur and these 4 oxygen are all covalently bonded together, so they're basically stuck together. So it's a group of atoms that share an overall charge. So they're a group of atoms that share a charge. That's what this says. And of course, we have a polyatomic ion sheet, so you don't have to actually memorize those. It shows the charges and the names and the formulas for a whole bunch of polyatomic ions. We see on here that the vast majority of polyatomic ions are negative, and really the only one that we use very often that's positive is ammonium, NH4, yes. All right, number 6 says you should be able to explain disassociation. Disassociation is the separation of ions in a solution. We saw this a lot with acids and bases, but any ionic compound can disassociate. Acids are, by definition, ionic compounds. So if we take this aluminum and this oxygen, and assuming it's soluble in water, I'm not really sure actually, but assuming it's soluble in water, if we stick this in water, the water molecules will tear apart the ions. And then we will have a bunch of Al+3 and O2- floating around in the solution. So as a compound themselves, there's no charge. These things balance each other out. But when they get disassociated, then the ions separate. So it's a separation of ions in a solution. Hopefully Mrs. Erickson is back there monitoring them. All right, and that's pretty much all there is. Oh, except I would put a check mark by number 2 and number 4. Okay, I guarantee on the test I will have a question that says something like, what's the charge? What charge ion will fluorine form? So you have to look at the periodic table until it's a -1. And I guarantee I will have something like this where I give you like aluminum and oxygen and ask you to write an ionic formula for them. So find the charges, put them down. I just put the check marks right there. 2 and 4. So glad you guys are here. We did not skip chapter 6.
Yeah, and it goes to 7.
Oh.
Yeah, Roark, get on the feet.
Uh-oh.
We can't have a test on chapter 6.
Oh, yes, we will.
No! You didn't put it on here.
All right, we will, I'll have, for tomorrow, I'll have a study guide for chapter 6. Sorry, that one apparently got left out. We'll go over that. So let's go on to chapter 7.
Yeah, Roark, you were giving me the sass, but it's not on here.
Chapter 7, you can Circle everything there.
Oh my god. Jeez. You weren't a shit when you said this was a semester final.
I was not.
This is stupid.
And you can also put a check mark next to everything there.
Oh. This must have been an important chapter.
Well, I mean, think about it. We've never really gone away from it. I mean, there was problems that we did in stoichiometry where I just gave you the names of stuff and you had to write the formulas. So there will be a section on there. There won't be too many problems, but there will be basically be an example from each where so that would be 3 ones where I give you the name and you have to write the formulas, and 3 ones where I give you the formulas and you have to write the names. Okay? So you have to review those rules. So for ionic compounds, remember that you just name the ions. Okay? There's no mono, there's no di, none of those prefixes when you're talking about ionic compounds. How do you know? If I give you a formula, how do you know if it's an ionic compound? Okay, how do we know there's going to be a cation and an anion?
There's no charges.
Well, I'm not going to give you any charges.
But you figure it out by using the charges on the...
You can a little, but the easiest thing is, if it's an ionic compound, there's got to be one metal or hydrogen. Basically, yeah, there has to be one thing from the left of the stair step and one thing either from the right of the stair step or the polyatomic ion sheet. Okay? If I give you something with only nitrogen and oxygen in it, that can't be an ionic formula because both of those things come from the right of the stair step. Now listen, there's really only a couple ways this can go. We can't have 2 of these things put together. You'll never see a formula between like potassium and chromium, 2 things from the left side of the periodic table. You can have 2 things from the right. So either there will be 2 things from the right of the stair step, okay, that's a covalent molecule, or there's going to be 1 thing from the left and 1 thing from the right, that's an ionic.
So for it to be ionic, it has to be from the left to the right?
You have to have 1 from the left, 1 thing from the left, and 1 thing from the right, or your polyatomic ion sheet.
And what's the name?
So those, you remember, you just name them, change the N to IDE. Sodium chloride, or potassium fluoride. Okay, calcium oxide. The tricky part when it comes to ionics is the transition metals, because remember those and tin and lead have varying charge, and that's where you have to use the Roman numerals. Okay? So remember, you don't use Roman numerals for these. You don't use the Roman numerals for bromine, aluminum, or gallium, but these have to show the charge. And tin and lead. So, SN and PB, 50 and 82. So, it would be a pretty good idea, I think, this weekend. And now you got the whole weekend to prepare. Not that many of you will. I would strongly suggest going to that section and do some of those problems just to practice. And all that stuff, remember, you can find on the website, too. Now, covalent molecules. If both things come from the right of the stair step, that's where you use the prefixes. Okay, so mono, di, tri, quad, or tetra, I mean. Penta, hexa. If both things are from the right. So if you had something like P6O10, I have no idea if that is actually a compound that can form. I sort of doubt it, but I'm making it up for the hell of it. Okay, what's the prefix for 6? Hexa. What about 10? Deca. So they're prefixes, remember? So, hexaphosphorus decaoxide. Put the prefix in front of the name. And as always, we're going to change the end to IDE. Okay. Well, you got to study and remember as much as you can. Acids. Remember, acids are always going to have hydrogen as the cation. Now, don't get confused. They can have hydrogen in other spots in the formula, but when it's listed as the cation, it's always out front. Sorry. Right. So I was going to give some example here, like this. Don't we all? Okay. So this has got hydrogens in here, but the thing that tells us it's an acid, there's one out here. If it wasn't an acid, then we would list this as C2H4O2. Okay? But the fact that we have a hydrogen right out front tells us it's a cation. This must be an acid. This must come from the polyatomic ion sheet, right? Remember, off the polyatomic ion sheet, no hydro, right? But we do have to change the end. 8 turns to ick, and OUS turns to ite. Thank you. Or I said it backwards. Ite turns to OUS. Hey, I am old. I had a momentary mix-up of ideas there. 8 turns to ick. 8 turns to ick. So sulfate in an acid is sulfic acid. Okay? Ite turns to OUS. So sulfite would be sulfurous acid.
Wednesday we're going to get through a lot while you guys are gone. And then you'll have to watch the video, I suppose.
Well, I think Wednesday we'll just take off.